Hello, this is the Independence Dimension Inequality Proof by Andrew Kenny, Christian Rave, and Kaylee Stelling. To start things off, the Independence Dimension Inequality states that any set of n vectors, such as a1 through ak, is linearly dependent when k is greater than n. That is to say, when the number of vectors in the set is greater than the dimensionality of those vectors. For simplicity's sake, in both parts of the proof, we will be setting k equal to n plus 1. And the two parts of the proof that we'll be doing are for when n is equal to 1 and when n is greater than 1. So the first part of our proof is for when n equals 1. K will therefore be 2, which means we will have two vectors, a1 and a2, of one dimension each. In order to prove that the independence dimension inequality holds here, we need to show that these two vectors are linearly dependent in all cases. Of course, when they're 0, they're going to be linearly dependent, but when they are non-zero, we can introduce scalars beta 1 and beta 2 such that beta 1 times a1 minus beta 2 times a2 is equal to 0. Pretty simple solution here. We just set beta 1 equal to a2 and beta 2 equal to a1, and we can see now that no matter what the vectors a2 and a1 are, the linear combination of them can be 0. That's the first part of the proof. We'll now go on to the second part. So the second part of the proof, when n is greater than 1, we will first introduce a set of n minus 1 dimensional vectors, which we will call b1 through bk, which were made by removing the last element from each of the a1 through ak vectors. We know that these are linearly dependent by our induction hypotheses. Their dimension is lower than k, which, according to the inequality, means that they will be linearly dependent. We can then introduce scalars to this new set of vectors such that not all of the coefficients are 0. That's from the definition of linear dependence. And we also assume that the vectors are set up in a way such that C1 is not equal to 0. We then introduce a second set of vectors, or scalars rather, which is d2 through dk. Again, d2 through dk are not all 0 because the set of vectors b through bk are linearly dependent. Okay, so we have the scalars c and d applied to the a vectors now. We know that if these final elements e or f are 0, then we have a linear combination of all 0 vectors, and we stated on the previous slide that at least one of the coefficients is non-zero, which satisfies our definition for linear dependence. If e and f are not 0, then we can multiply the first equation by negative f over e and add it to the second, which gives us this equality here. We see that on the right-hand side, the negative f over e times e plus f will reduce to 0. And because e and f are not 0, the first coefficient, negative f over e times c1, is a non-zero value as well, which leads us back to the linear dependence definition. And we have now proven in all cases that a set of vectors will be linearly dependent when the number of vectors is greater than their dimension. And we will now show some two vectors to demonstrate this proof.